Today, I'll be reviewing a paper called Metalearning Framework with Applications to Zero-Shot Time Series Forecasting. This paper is on arXiv, and if you're interested, please take a look at the link in the description. I'm not the author of this paper, I'm merely reviewing it to learn more about it. This is about a deep learning architecture used to forecast what the next values of a sequence are going to be without explicit retraining on the target data. This expands on a previous paper by the same author, which introduced the NBEATS architecture, a deep neural network architecture for time series forecasting, which aims to beat the state-of-the-art on datasets such as the M4 competition. Time series forecasting. Time series forecasting is used to predict sales, demand, supply, time to arrival, and valuable information used in business and in decision-making process. Before an untrained deep neural network provides useful forecasting, it should be trained on a large time series dataset. The authors tested out pre-training on two datasets. The first one is the M4 competition dataset with thousands of time series. The second one are financial time series from the US Federal Reserve. From time to time, there are interesting competitions on time series forecasting. Perhaps the most important and most known, the M4 competition showed a winning solution to be a hybrid between a neural network that used residual architectures and attention as well as LSTM, combined with the classical old winter statistical model. Some authors argue that hybrid approaches and combinations of methods are a way forward for improving forecasting accuracy and making forecasting more valuable. Machine learning can forecast time series better than classical models, provided there is enough data for it to train with, which is not the case for most of the M4 competition dataset. Most of the time series in this dataset are actually very short. Most time series, which are yearly, quarterly, and monthly, are very small, usually with less than 300 instances per time series. This might be a problem for the data hunger that deep learning has. The time series with frequency, weekly, daily, and hourly are fewer, but typically have more instances. In order to be able to compete on these datasets, practitioners have resorted to more complex approaches, such as using residual neural networks, which are able to deal with time series with reduced length. Okay, but how does metalearning help us in this problem? Metalearning, or learning to learn, is usually described by two things. First, the accumulation of knowledge across tasks. It's also known as transfer learning and multitask learning. Secondly, by quickly adapting the accumulated knowledge to a new task. Task adaptation. Say you have a time series, such as the sales of beer. If you train a neural network on this data and apply it to the sales of beer as well, you are doing machine learning. If you train a neural network on the same data of sales of beer and apply it to predicting gross domestic product, you are doing transfer learning. When doing so, you don't retrain the whole neural network, you simply use it on this new data. By doing so, you are doing zero-shot learning. Zero-shot transfer learning is a subset of transfer learning and of metalearning. Learning how to learn with no example of what the target distribution is from a dataset that you don't know. Zero-shot learning is machine learning that deals with predicting the target variable of a dataset you have no idea about. You can train a model for a general purpose and then apply it to a more specific problem. This is similar to transfer learning in image processing, where we can start with a pre-trained network which is already capable of recognizing some shapes and forms, such as lines and particular densities. This provides a warm start in case we want to classify whether the image that we're evaluating is an image of a cat or a dog. The authors of this paper are basically looking to find a general purpose model that is able to forecast anything, based on the information that you feed to the model just before prediction time. Residual connections act as a metalearning adaptation mechanism, expanding the expressive power of the architecture on the fly. Just feed it a time series and it'll get a prediction straight away. No training required. This is a neural network based on backward and forward residual links composed by 30 blocks, each having 4 fully connected layers with 512 neurons each. A previous reviewer questioned whether the current architecture is actually better or whether its performance is simply justified by having more parameters. In fact, not many parameters are needed and they can actually be shared across blocks. The results imply that NBEATS is able to compress knowledge about a given dataset in a single block, rather than in 10 or 30 blocks with individual weights. because the difference in performance is small, the weights are shared between the blocks. This is good for applications where storing neural networks efficiently is important. Here we can see the parameters used to train a model. A learning rate of 10 to -3 is used, and a batch size of 1024 is used. The look-back horizons vary with the datasets used. After 5 epochs and 15,000 iterations, our model is trained. Results are really interesting. The N-beats that was trained on the M4 dataset works pretty great on the remaining datasets. However, I can't help but to think that maybe the N-beats underwent a lot of hyperparameter optimization in order to reach such a good result out of sample. It will be interesting to see how many combinations of hyperparameters the authors actually tested in order to rule out the multiple hypothesis problem. How can we replicate this experiment? There is mention of a repository with these experiments. You can also use the N-beats implementation from the GuluNTS library. Limitations: time frames and frequency of input. I get using a model that's been trained on an hourly dataset and applying it to a monthly dataset after interpolation. But what the authors are doing is the opposite. They feed hourly data to a model that has been trained using monthly data. It would be nice to have more details on this bilinear interpolation. But I'd like to know why the authors use bilinear interpolation, which is not clear to me. Bilinear interpolation is an extension of linear interpolation for interpolating functions of two variables, say x and y, but in this case we're dealing with univariate time series. Out of sync. These experiments use the M4 dataset described here. There isn't a clear cutoff point between training and testing. Unless there is a clear cutoff point, you are cheating when you train your model. In fact, the official site for the M4 competition states that the original dates were not available to the participants. Imagine trying to forecast the year 2001 when you already have data on 2001, 2002 and 2003. This is cheating. Conclusion: it is viable to train a tabula rasa neural network on a large time series dataset and deploy it on a different target time series without retraining. What about time series with many dimensions? Is it possible to apply this to multivariate time series?